All right, folks, thanks for watching my video. I appreciate it. Let me just make sure my mic is working. Yeah, it is. It looks like it is. Um, hey, would you take a moment and set up some notes for me? We're going to be talking about 9.3. We're going to skip 9.2 for today, and we'll come back to it. Okay, so we're going to talk about 9.3, which is all about complex numbers. And it might not feel like polar representation or polar concepts. Like, what complex numbers, what do they have to do with polar? Well, I'm going to show you. All right. I'm going to show you. Today, maybe we won't see an application of like, why is it better to write a complex number in polar notation? But I want you to understand that, look, this is a complex number. Hey, look, if you haven't set up your notes yet, put the video on pause, because I don't want you copying stuff down here and then you look back here and go, what was he talking about? Okay. Hey, thanks for doing that. Thanks for putting the video on pause and setting up your notes. All right, so this is a complex number, right? And where do complex numbers come from? Where have you seen them come from? Well, quite often they'll come from the quadratic formula. So imagine you've got the opposite of b being 5 plus or minus the square root of b squared minus 4ac. And the b squared minus 4ac comes out to be negative 4. And then all over 2a comes out, let's say, to be a 1, right? So how does this all simplify? Well, 1 goes into 5 times, plus or minus. And then the square root of negative 4 is the same thing as the square root of negative 1 times the square root of 5. Okay, and we've divided, why did I put a 5 there? Sorry, a 4. Oh, sorry. We got a 4 underneath the square root sign. And so, or negative 4. And so I got now the square root of negative 1 times the square root of 4. And the 1 divided into whichever one you want to think about. I mean, the 1 in the denominator doesn't really impact things, right? So how does this simplify? Well, we get 5 plus or minus, and then the square root of negative 1 is defined to be I. Okay, that is I. That's by definition. So, okay, defined definition is the square root of negative 1 is equal to I. That's what mathematicians said. Now, square root of 4, we all know what square root of 4 is. That's 2. Now, we probably put the 2 right there because the square root of 4 is 2. But a lot of times we'll just put the constants in front of something that looks like a variable. Now, I is not a variable, but it is still a letter, of course. And so usually we put the 2 in front of the I, right? This is called a complex number, and it's 2 of them, actually. 5 plus 2i, 5 minus 2i. The word conjugate is used to describe these two numbers. The only difference between the two numbers is one is a plus and one's a minus in front of the imaginary part. So real numbers look like this. Complex numbers look like this, a plus bi. And they always come as pairs. So you'd have something like a minus bi as well, particularly when you're talking about quadratic formula, quadratic equations. Complex numbers will always come as pairs or polynomials or whatever you got. So this 2 plus 3i would have a partner, 2 minus 3i. Now, we're not going to talk about that partner right now, but because our main goal is to represent this number in polar representation. Well, first we got to understand this. Mathematicians would graph this number. I know you're like, what? It's just a number. What are you doing with two axes? One this way, the x-axis, and this one going this way, the y-axis. Well, this axis down here is the real axis. Okay, that fancy R is representing the real. So the A part is the real part. You can see it's a 2, right? So they would say, well, we're going to come over 2 spots on the real axis, and then this part over here is the imaginary part. Okay, so imaginary axis, or the I part. All right, and so let me just put like maybe I out here. So we're going to go up 3 spots on this axis, 1, 2, 3, and then we come over to this point, over 2, up 3. This point represents 2 plus 3i. Now, doing arithmetic with 2 plus 3i is easy if you're adding complex numbers. So let me show you some arithmetic here. Give me like 30 seconds, okay? Arithmetic. I hope I'm spelling this right. I don't think I am. No I in there. Arithmetic. I don't know. Whatever. Doesn't matter. Now I'm embarrassed. I got this on video. You can show mom. Say, geez, man, he doesn't spell very well. So let's say you're going 2 plus 3i, and you want to add that to 5 plus 7i. Okay, well, it's super easy to add complex numbers. You just add the real parts, you get 7. You add the imaginary parts, and you get 10i. I mean, that's ridiculously easy. No one needs polar representation for that. Let me show you a place where you would need polar representation. Let's say you had 2 plus 3i, and you want to raise it to the fifth power. Holy moly. If you had it like this in rectangular format, you'd have to go 2 plus 3i times 2 plus 3i times 2 plus 3i. I don't have enough space here. I'm just going to emphasize this point, right? Okay, so I'm going to take some time here. 2 plus 3i and 2 plus 3i. Oh my goodness. Can you imagine distributing this through like this, and then adding all the like terms? And oh man, it would just be such a pain to do. So we need polar representation to do a problem like this right here. Okay, and we're not going to talk about that today. Like, how do you do 2 plus 3i to the fifth power using polar notation? We're just going to convert to polar notation. So look, we're going to have an r. The r is this distance, like we did before. Geez, I'm trying to make that a straight line. I'm doing a horrible job. Let me try again here. That distance right there is our r value, right? And then this is our theta. And when it says the argument needs to be in terms, or like in degrees, what they're saying is, and in our homework today, is that put theta in degrees for these homework problems. Unless they state otherwise, we're going to put them in degrees. Okay. So how do you do that? Well, I think you guys have some skills already in how to do that. Like, if we're going to look for the r value for 2 plus 3i, okay, so 2 plus 3i is in rectangular format, meaning you go over 2 and you go up 3. We don't know what the angle is yet, and we don't know what the r value is. Well, we would just go like this. 2 squared plus 3 squared, right? That's what r squared would be equal to, because r is the hypotenuse for a right triangle with legs of 2 and 3, right? So I'm doing Pythagorean theorem. So I get r is equal to the square root of 2 squared. I don't like that 2. Let me do a consistent here, like this format, 2 squared plus 3 squared, okay? And so that gives me the square root of 4 plus 9, doesn't it? Hopefully I've not lost focus here. Square root of 13. All right, so my r value is the square root of 13. So let's put over here, 2 plus 3i is equal to the square root of 13 times, now here's the weird part, cosine, and we're going to find out what theta is right down here. Okay, so we're going to do the theta part here in just a second, plus I sine. And the theta that we find is going to go right here and right over here. Now, why does that make sense? Well, if you take the cosine of the angle, that's what the x component would be in the unit circle. And then if we multiply it by the square root of 13, it's gonna crank out to 2. I mean, it will if we do this correctly. And then if you did square root of 13 times the sine of whatever angle we get down here, it'll give you 3. So it's really representing the same numbers, 2 plus 3i, but it's representing it in a different format. And I'm not going over how we're going to apply this, but it has to do with this like fifth power idea. It's going to be super easy to raise the complex number to the fifth power if we have it in polar notation. And you might say, I don't believe you, Nelson. I understand that. You might not believe me, but it will be. Okay, so trust me on that. So how are we going to get the angle? We've got an opposite leg of 3 and an adjacent leg of 2. So tangent, right? We're going to say the tangent of theta. Let me come down here. We got a little bit of space. Tangent of theta is equal to 3 over 2. And then to get theta, we're going to take the inverse tangent. So inverse tangent of 3 divided by 2. I'm going to jump over to Desmos here. Let's do that right now. Everybody do that with me, Desmos. And I want you to watch this, so don't look down at like your paper to take notes for a second. Make sure you change to degree mode, right? Because if you don't, you're going to get the wrong answer. You're going to ask me why, and I'll help you if you get it wrong. Okay, so inverse tangent, and we said we want inverse tangent of 3 over 2, right? So I've got the inverse tangent in there. I arrow to the right to get out of that little kind of exponent superscript, and then I'm going to go 3 divided by 2. I got 56.3 degrees. Okay, so I'm going to round to the tenths place. So let me put a little dot over my equal to and put 56.3 degrees, and then I'm going to come up here and put 56. Oh geez, I don't have enough space. And 56.3. Sorry about that. Hopefully you can zoom in. Hopefully you can see that. Let me just make sure I have the right number here. I do have 56.3, don't I? Right? And I did inverse tangent of 3 over 2. Okay. Hopefully I didn't make any mistakes. This is what we're going to be doing on our homework today. We're going to convert from rectangular form to polar form. And call me over if you need some help, okay? Thanks for watching the video. I appreciate it.